Okay, good morning everybody. Welcome to the second day of the graduate school. My name is Ruben Wiersma and we organize this graduate school together with Mark right here at the front. Today the program starts with a really nice talk by Amir Vaxman about directional fields, and I'll just give him the floor right away. Okay, Amir?
Okay, hi everybody, I'm Amir and thanks for Mark and Ruben for inviting me. I gave versions of this talk in a few years in the last decades. I keep updating it according to new stuff, but I also keep it very basic because it's a summer school thing, so I want to always learn people the basics and they don't change a lot. One of the disclaimers that I'm probably going to overheat in the middle, but hoping you don't notice. So I keep referring to kind of, let's say, code/class name examples from my library Directional, where a lot of those things are implemented. So without further ado, let's begin. First of all, what are directional fields as a definition? So we called an n-directional field, n being kind of a degree. Basically, given some kind of domain, shape, or volume, or otherwise, for every point, we attach n vectors. That's an n-directional field. So we all know the classical version, like the one-directional field, which is essentially just a vector field, like wind fields and flows and all those kind of stuff. It can be on spherical domain. But in geometry processing, we have other variants that are important for us. For instance, we have some kind of two-manifold in 3D, this surface, the rocker arm, on which we have kind of a tangent field that I'm going to be discussing. It's a four field because in every point we have four vectors pointing in some direction that are tangent to the surface. But then in the volume itself, like in the actual volumetric 3D, there's some kind of volume bounded by boundary surface. And inside, there is kind of a three-dimensional cross, six direction at that point. So that's a three-dimensional frame field. So this object is very, very fundamental, very foundational to geometry processing. You see it basically everywhere. Sometimes it's used without being called this way because it's classical. So hair patterns, flow patterns, magnetic fields, deformation fields, even traffic. Okay? So those are many usages. I'm not going to discuss so much applications today, but more about how do we work with such fields. And one of our core applications that we're going to be discussing is meshing. Okay? So by meshing, we follow a very specific pipeline. We always follow kind of the same one with some variations within, in which you have some input mesh, usually a triangle mesh, because that's what we get. And the essence of those algorithms for directional fields are computing some tangent field on it. What kind of field? Such that its directions align with the directions of a mesh that we want to see eventually. So for this field, we integrate it, and I'm going to discuss this a little bit, into parameterization. So a collection of scalar fields that trace the surface using their level sets. And then the step which is, let's call it theoretically trivial, but geometrically the hardest maybe, is the meshing. Taking the parameterization and making it into an actual mesh. And you see that the directional field and the mesh look kind of the same. So it's plain to see what we're trying to optimize for. But of course, this is not limited to quad meshes. Also, triangle meshing can use this by taking directions that have kind of a free symmetry. Okay? And in 3D, we often refer to hex as in hexahedral meshing, where we have like 6 directions at each point in some kind of domain, and then we integrate them. Okay? By integrating them, we means we kind of trace their directions, and from this direction, you can already see the resulting mesh that is going to happen, which is basically tessellating the original domain into a set of cubes that follow those orientations. Okay? So meshing seems like a relatively simple application, but it's actually a very, very diverse thing. Okay? Basically because we usually want meshing with special functions because they have to meet some criteria. For instance, a lot of the time for architecture, we want meshes that have planar faces. So we want quad meshing, but the quads themselves have to be flat. So not every directional field will lead to this. We need kind of special form. Or that the mesh that we create has to be geodesic, which means those lines we trace on the surface have to be non-twisting in a way, so you can make the mesh with kind of bands for instance, by kind of wicker or anything else. Okay, so this requires a special design already in the directional field stage. Okay, but there are, of course, more. We can create fields that will lead to a mesh that is developable, which means we can open it up without stretching or any deformation to the plane, or use a field to guide some kind of stitching pattern. For instance, we have a piece of fabric, we can do what's called smocking, in which we stitch the pattern according to a given directions that were given by this kind of alignment, and then we get a surface that is made out of it. But those fields can be used to many other purposes. For instance, we can theorize how they work differentiably in the language of currents to create minimal surfaces. Okay. So I usually show those examples on fields that have some kind of inner 1 or 4 symmetry, but we have many other symmetries that pertain to many other applications. For instance, stripe patterns, those have 2 symmetries, or those kinds of patterns, or even higher ones, 5 or 7, that can lead to all kind of quasi-crystal formations or Penrose patterns. Now, we can use also fields for things that are not necessarily meshing. For instance, illustrations, or the kind of auto-completing illustration where someone only does several lines. Those lines are directional. That means they mark the direction of the shape they want to be. And we somehow find a way to interpolate this, or maybe sharpen the line, to find kind of a vector representation of this, or fill it out with some kind of diffusion curve. And otherwise, we can of course use fields for, let's call it, a more traditional, not necessarily geometry processing purpose, which is simulation. Use actual discrete representations of vector field to do simulation that is structure preserving, and by structure preserving I mean it preserves the physical and differential properties that we need. For instance, fields that are wind, they have to preserve mass because they're moving air around. So they have to do it also in the discrete setting for simulation, otherwise it violates the physicality. Okay? Or for instance, for fluid simulation, it's the same thing. You basically need to preserve mass, you need to preserve momentum, all those physical properties have to also be met in the discrete setting. And of course, you cannot have a lecture nowadays without having a slide with the word learning in it. Okay, so we do. Although this is not center stage at this one, you will have other lectures in the graduate school which will target this a bit more. But of course, as a kind of a foundational object of geometry processing, we know or struggle to learn them, yes, on surfaces, to understand patterns, to generate, for instance, deformation, to generate geometry with specific alignments, to generate features, and so forth. Okay. So before we target how we work with them discretely, we have to understand some continuous properties. I assume some of this will not be entirely not familiar to you, but let's call it revise them shortly. Okay? I will mostly be discussing surfaces, but we will talk about volumes in this lecture in some parts. Okay? So on surfaces, a single vector field is quite a simple object. You have some surface, there's a vector field that is tangent. Okay? And we'll talk about what tangent means here. But from this, there's already a lot of structure. For instance, you can see this object. What you can see is there's some kind of symmetry created on that object that reflects the symmetry of the object. There is some kind of vortex, a singularity somewhere in the middle. Okay? And even though this is a discrete setup, so you don't see a vector field continuously, you as a person can see the flow in the vector field when you're looking at it. Okay? So there's some kind of a discrete setting of this vector field, some kind of smoothness that allows you to see what it's up to. Okay? Two rotationally symmetric fields, yes, this is the contraction rho z, are just so that you don't know the sign of the field. So there's a flow, but it can be multiple signs. So there's an alignment to a line at this point. And a 4 rho z field is such as there's a cross. So there's an alignment at this point, but it's not clear which of any 4 directions it can be, like a quad, basically. And this is what it's for. But you can represent any non-symmetric field to your liking, like literally any collection of points, or even with some symmetry, but not all symmetry. For instance, there's a field here where you have 3 vectors. Each of them has a sign symmetry, so there's 3 lines, basically, but they're not necessarily symmetric with each other. They might have some kind of opening symmetry if you need it, so there's some kind of contracted hexagon, but not necessarily more than this. What do you use? Entirely application dependent. It's what you need to generate from this as an alignment. Okay, let's talk some more formalities, okay? To understand the meaning of the word tangent director field, we need an extra structure that is called the tangent bundle. Okay, that's an extra structure. You have a surface. On each point, you have kind of a vector space, which means the osculating plane in generic 3D differential geometry. Okay, that is the tangent bundle, which means on every point you have this plane. You can put vectors inside that plane, and the collection of all those planes is the bundle. That's a tangent bundle. So a vector field, sometimes known as a section, but I won't use this nasty word anymore, okay, is basically an assignment of vector per such tangent bundle, okay, to the ambient space. All right? So one other way to say that it's tangent is kind of go what's called codimension. So it means the tangent plane is a plane, yes, but tangency is defined by orthogonality to some normal. So you have in each point a normal, and all the vectors that are orthogonal to it are tangent. Those two seem equivalent, but not exactly. One of them is the first is intrinsic and the second is extrinsic. Okay? How do we do representation? And I will come back to this point also a bit later. So if you have a tangent vector field, it's in a subspace. It's in a tangent that can be, for instance, 2D in the 3D space. In order to represent it directly without any normal components, you need local coordinates, local 2D coordinates. They can be either Cartesian, which means basically some kind of local xy. That can also be interpreted as what's also called as a complex structure, which means there's a complex representation to this, x plus iy. Okay? For a lot of applications, and I will actually use this interchangeably. Yes, it matters a lot. But you can also use it as a polar representation, which means there is some kind of x-axis, and the vector field is defined by the rotation from that axis in the local tangent plane, around the normal, with a magnitude and an angle. Both of them are important for specific things. There's not one of them that is like more superior than the others. They're complementary. All right. And now comes a problem, which is actually not a problem. This is something natural. You want to do, when you do differential geometry, you want to do differential. That means basically you want to be able to compare between vectors in, let's call it neighboring or close by tangent spaces. Otherwise, there's nothing that connects, literally, I'm using the word connects between things nearby. Okay, so how do you differentiate vectors on 2 points on the surface? So one might say, let's just take a basis that is the same for all of them, but it's not possible, and there's not obvious definition of what is the same when it's curved. In the plane, there's kind of a sameness, but not in something curved. Like, who gets to decide? And that's actually an important point. Okay, so, but it's not mean all is lost. What you basically need to know is that if you have those two of them, yes, and I'm referring to it discretely because it's easier to work out, but this is a continuous thing, yes, like some direction. If you have two of them and you want to compare vectors to see how they changed when you move from one to the other, you just consider how the local basis changed from one to the other. So we have a notion of covariant derivative. That covariant derivative measures how much a vector actually changed in some kind of definition of actually. It's comprised of two components. Okay? So it's, first of all, it's a longer vector, which means I'm at a point, this green one, I'm looking how much the vector changed when I move along this direction, W. So, first of all, it's just the derivative. Okay? So I'm deriving the vector according to a direction. This is directional derivative, taking the gradient of the actual xy of the vector. But now I also have to correct this according to how much the coordinate system changed. That's the covariant part. So I'm also looking at how much the xy of the coordinate system changes, rotates, as I move along. Okay, so there's some kind of, let's call it angular velocity of the basis that changes with me. So what I'm checking is how much the vector actually kind of changed in space when I'm moving. I'm checking how much the coordinate changed according to the basis, plus how much the basis itself changed, which also smells like a chain rule, and it is just a chain rule, okay, basically. Okay. So, for instance, the covariant derivative is entirely zero. The vector fields are entirely parallel when you look at them closely, when the only rotation in the vector field that was achieved is literally just a change of basis. There was no actual, ambient change in this. Okay? Consequently, we can define the concept of parallel transport, which means zero covariant derivative. So you're an ant, you carry a vector, like it's always your right hand, you're moving along some kind of vector, and you're still keeping your right hand, so it's going parallel along the surface. That means covariant derivative 0. Okay? Now the question is, can I just take a vector and walk around in some kind of parallel loop and get myself the same vector? The answer is no. You know all those riddles, you went north, you went east, you went south, you didn't reach the same place, where are you? That's exactly this. Okay? So imagine you're at some point on Earth, you're walking east a quarter of the way, you're walking north, you're turning, you're walking south. Okay? You began with a vector that points east, you ended up with a vector that points south, although you were totally parallel, just because of the rotations you had to take to move around. Okay? So this notion of coming back to the same place but changing your orientation is called the holonomy. Okay? So the transport is non-trivial. When does it happen? When you have something called a Gaussian curvature, which means the surface you covered while walking the path has some curvature inside it. So if the path is simply connected, which we'll assume, okay, like the angle you ended up minus the angle you started with, including any full rotations, yes, is the Gaussian curvature. Now you're going to ask, what is this measure of Gaussian curvature that I can use to do this? In fact, the answer is the other way around. It's the connection that defines the Gaussian curvature. Okay, Gaussian curvature is more primitive than other things. It's defined by the holonomy. Like if you want to know what's the Gaussian curvature of any kind of surface patch, you walk around it and you measure how much you changed in rotation. That's a definition. All right. Okay, but if we have an actual vector field, like already existing, there's a point. I'm not moving in a parallel transport anymore, forget it. I'm moving in a way that I keep rotating around so I match an existing vector field. Okay, so I lost the parallel transport. I do return to the same place though. Okay, but there is still some degree of freedom when I return to the same place, and that is how much full rotations I had while doing so when I moved in a cycle. Since it's an existing vector field, it's always integer, because when you walk and you always move your arm to match an existing vector field on the surface, you will return to the same vector field, but you might have rotated around yourself a couple of times. Okay, so it's always integer. So, for instance, you could have moved around a vortex like this, okay? And if you count how many rotations you did, it's exactly 1. So the index of this cycle is 1. Okay? The index of this is also 1. You still rotated around yourself 2 pi times. Okay? Although this is a vortex and this is a sink, it doesn't matter. It's about how many times you rotate against yourself. Okay? What is the index of this? Assuming closest rotation, which is not an obvious assumption, as I would say. Yeah, 0. Like you basically just moved around like a metronome, yes, without doing much damage. And this is a -1, actually. You kind of moved against the direction when moving counterclockwise. And you see it looks a little bit hyperbolic, like there's 2 directions moving in, 2 directions moving out. It's on purpose. And of course, every integer is possible. You could rotate 2 times, -1,000 times, and so forth and so forth. And after a while, when you look at it, you immediately see the index. You can see in your eye how many twirls you have and in which direction. Okay? So, those points that have like non-trivial rotations, like all of them except the second from the right, are called singularities. Okay? When you look at the surface, you immediately see them, where you have those singularities, and they don't distinguish between source, sink, or vortex. Now, one question that begs is, can we have all manners of singularity on the surface? Can I just put like a zillion pluses or a zillion minuses or so forth? The answer is usually no. The sum of indices, yes, is what's called a topological measure of the surface. It's 2 pi Euler characteristic, where the Euler characteristic is just 2, an actual 2, minus 2g. G is what's called the genus of the surface, how many handles you have. Formally, a handle is some place that you can break without breaking apart the surface. So if you can break a surface apart some g times, then it has genus G. Like a coffee cup, you can break it once, it's still intact. Break it twice, it's not intact anymore, it has genus 1. And a pretzel, if it's welded, not a knot, you can break 3 times. Okay? B is the number of boundary loops. So you see the bottom one and the windows and so forth. There are also loops on their own. Okay. Right, so I hinted at this, but I'm going to derive it the other way around now. So I said, okay, let's forget parallel transport, let's walk on a vector field, rotate with the vector field as we're moving around, and get those singularities. So one could also think about a vector field, and that's actually a classical one, as defining its own transport that is not parallel anymore. So when you go around and you rotate, this rotation is built in. So the connection measures how much neighboring is parallel, and the vector field is a deviation from parallelity. Okay, so we define a new parallelity that is the already given change by a field, and the connection is trivial in the sense that every walk around every cycle either adds up to 0 because you keep rotating to offset curvature, or an integer because you add the singularities. You're walking around and it's non-trivial. Okay, that's called a trivial connection. Okay, so this new curvature that is induced in the left one is 2 pi, because I walked around the vector field and rotated once. And the curvature induced by this non-singular point is just 0, because you return to the same place. Okay. The interesting part about this is no matter how you define the curvature, as long as it's consistent like this, as long as the connection is symmetric, it's still the same. So the total curvature of a vector field and the total curvature of a surface, or more aptly the curvature of the tangent bundle, equals the same. So basically, what it means is some kind of transport thing, in a way, if I have to be a little bit deep about this. A vector field changes parallel transport. There's a deviation, but the deviations, they add up to 0. Okay, if you create a deviation here, the deviation in the other direction is negative. So it's like taking a surface and you're mutilating it, but the total curvature is the same. That's basically what you're doing here. Yes, like changing a vector field from being parallel is kind of mutilating, deforming the vector field. Mutilating is not a nice word. But the entire curvature is still the same. Okay. Now I will return to a little bit to application. That was a bit of theory. So what happens in n fields? Like if you have several directions per point, so luckily exactly the same except everything is fractional. Okay, so you have a vector field returning to itself, but it doesn't have to go full round to return to itself because we don't care which vector it's which. We have something that is called kind of ticks, like in an old 70s phone. Okay, so you have a cross and you tick it once and there's like a fourth rotation, but it's still the same kind of object. Okay, so singularities can be fourth. So those things seem like weird, but that's actually a little bit more intuitive to us, because if you think about a cube, like a corner of the cube, you stand on a face, you climb up, and then it's direction in that direction. You did exactly a fourth rotation. So a cube looks like those kind of fields. Okay? Or if you're building something from Lego and there's kind of a corner inside, it's actually a 5 because there's 5 faces facing it. So if you walk around it, you'll see that you rotated a quarter in the other direction. All right? So those are those kind of singularities. The red ones are positive, and like the corner of the cube, and the blue ones are negative, like this corner of the Lego face, the knee of the Lego. Okay? And the entire curvature discussion is exactly the same, except fractional. Okay? So if you had to add up to 8 positive full integer singularities, sorry, to 2, because the Euler characteristic was 2. Now you have to have 8 of those, because each one of them only carries a quarter. So it's still kind of a mass transport discussion. Yes, where curvature is kind of a local mass. Okay, and that's exactly how they look like. Another interpretation of this, also a classical one, is that 0 is just like a piece of fabric. Okay, and as positive as you go, it's like you cut off one piece of the fabric and stitch the rest together. You created kind of a cone. Okay, so a fourth is indeed you cut off one piece, threw it away, connected, and this, what's called the lemon singularity, the half, you cut another piece and tied it up. And negative is the other way around. You cut a seam and you added a piece of fabric inside it and it pringled up. Okay? So you're getting a fourth and a fifth and so forth. All right. This was about the continuum, and let's talk about how we actually do those things on surfaces. First of all, when we do discretization, we also have to address what are the challenges. Why is it not obvious to just take continuous definitions? So the first and foremost challenge is that it's just discontinuous. Okay, you don't have any notions of derivatives, any notions of derivations, or so forth. Those things don't exist. You have to make up for it in some kind of way. Okay, so that is always the case for things like finite element or anything in geometry processing, but vector fields carry their own extra difficulties. So one difficulty that we will address is connection. So I discuss connection as like you're an ant walking on the surface and your coordinate system gradually changes with you as you move along, but this is not the case. You have like one point and then you hop to another point. So you need to address what's the connection here. This is not a big challenge. You can already probably see the solution, but still it is one. Okay? And the other one that relates to it is that when you walk around the cycle and you have a vector with you, it also gradually changes. Now suddenly you had those 4 vectors. You jumped along to the other one and like, wait, where was the vector I was holding on to? Now I have 4 of them. Which was the one that I was addressing? And that's actually important. So that's called the matching. Okay, like which of the 4 goes to which of the other 4 when I'm doing this. But then even after that, there's the notion of interpolation. Like what would you assume? This is a sampling problem. What would you assume that happened between those 2 if you needed to? So you can say, okay, the first vector was this and the other vector was that. I kind of have the handle of business because I'm assuming it had some kind of, let's call it shortest rotation, like the least effort kind of way. But it's not necessarily the correct choice. Sometimes you do want for this to happen. Okay? This full rotations that you kind of lost. This is a sampling problem. That means it doesn't go away. By the fact of using something discrete against continuous, this is like below sampling frequency in a way. Okay, so let's address all of this. Okay, I will sometimes refer to classes like this because the way I build directional is very abstract. It builds it like some kind of representational classes on which you can dress meshes to use it. So instead of a continuous tangent banner, we have a discrete one. And what is it? It's basically a graph in space with nodes and edges. Okay, the nodes are tangent spaces, which means there's attached some kind of plane to them that you can represent a vector. And the edges are adjacency relations, okay? Which means this one is adjacent to that. It connects to that. It won't connect to anything else. Okay? In every node, you can use any intrinsic coordinates you want. It's just a plane like any other plane, except it's discrete. All right? What is the discrete connection? It's actually quite a simple generalization. It means that you have some kind of number or rotation matrix, but I will express it as a complex number. It's easier on every edge of the graph, telling you the coordinate system of this one became the coordinate system of that one by this rotation, which means if a vector field is multiplied by this rotation, you get the parallel one on that face. Okay, and that's all you need from a discrete connection. In fact, this is quite enough for most of what I've shown you before, this structure. Once you define this, you're done. There's a lot of stuff you can just derive from this, as I will show you. Okay? And then there is the question of matching. Okay, so for a single vector field, it's always, there's one, so it goes to that one. But what happens if you have 4 vector fields on that one and 4 vector fields on that one? Who goes to whom? Okay, so that's actually a question that 12 years ago we realized is not that obvious. Okay, so one assumption we always make is order preservation. That means the vector fields will be arranged in some kind of counterclockwise against the normal, and they will go as one unit like this. So this reduces the choice to one-dimensional one. Pick a vector, take it to any other vector, and the rest follow in a loop. All right? So that's a one-dimensional choice. You still have n choices. So the question is how to make a choice if you need one, if you want handed a choice already. So let's call it not obvious but intuitive choice is what's called the minimum effort. So if you're taking those vectors to those vectors, figure out the choice that rotates everything the least, right? Where also the rotations have to be signed. So there's like a back rotation, which is a minus, and a front rotation, okay? And then the effort of this choice is the sum of all those angles. How do you make the choice? Because you can enumerate all those n choices. So what's interesting here is that every choice is differentiated from any other choice by exactly 2 pi. Because once you made a choice, the cost of the other choice is again 1 full tick, where the effort is just rotating the sum of which to 2 pi. Okay? All right, so what? Once the choices are enumerated by multiples of 2 pi, there's always one choice that is between minus pi and pi, and that's called a principal choice. Okay, so that's called a principal matching. There's always exists one, and it's always unique, except if the vector fields are exactly orthogonal to each other, like a plus and an x. Then you have 2 choices that are equivalent. You're exactly on the cusp. If you have those things, something is really wrong in your discretization because they're like the least smooth vector fields ever. So you don't want them anyhow. You do something else, okay, if you reach this situation. So there's some pathology in your mesh. Okay? And then there is the actual rotation. Okay, so this was the choice of who goes to whom, but there's how many times does it does this before you do that. So there's valid rotation choices that are encoded by another integer, like a full integer, which is, again, some kind of least effort rotation versus any other wild choice. Okay? Which is called a period jump. If you don't know what happened in between, like you didn't prescribe it, you only got those 2 vectors, the only thing you can do is assume principal, which means the least movement. Yeah, you cannot do any otherwise. But if someone gave you the choice, then you can do it. Now, you would ask a question, why do you even bother explaining this to me? Who wants those huge choices? Well, in fact, it's sometimes a must, because a lot of meshes have like really low valency in vertices. So that means you have like a vertex with only 3 triangles around it. And you still want a lot of action to happen in between. You want to encode it in some way. If you only assume the implicit choice, the action is very limited between one triangle and the next. So what you will see is that if you want to have an algorithm that wants to put a lot of curvature in that point, instead of a single huge singularity, which is nice, you get like a lot of them spread out along the, it's kind of a sampling artifact, which is totally unmeshable. It's totally useless. So actually, sometimes you want to be able to prescribe this directly. Okay. So what do we do about those curvatures and stuff like this? We need an extra structure on the tangent space. It's not enough to have edges. You also need a notion of kind of faces or cycles, which means you need something to say, well, those are an existing cycle. There's some kind of progression of edges with a local disk topology, which means the cycle is simple. That gives it the 2-manifold structure. Okay, so you're saying, okay, how is holonomy described? Simply by aggregating the rotations over and over until they reach the same point. And then I have a notion of Gaussian curvature defined by the connection, not the other way around. Simply by the argument of the order rotations. Those are complex number. I take the argument, which means the entire rotation that happened. Okay, so it gives me this angle, eventually. And that is the Gaussian curvature of this tangent space. Now, kind of a trick thing here is that if you define the tangent bundle to be exactly like the normals of some surface, you will reproduce the Gaussian curvature of the surface, but not necessarily. Like one example that I also realized is that you can choose it totally arbitrary. Take all the normals to be the x-axis. Even though you put it on a surface, the Gaussian curvature is flat. Like there's no rotation anywhere, you're just moving stuff around. Okay, so actually, the Gaussian curvature derives from the way you did the tangent bundle. Yes, and the Gaussian curvature of a surface is because it has a specific tangent bundle. So what I wanted to say is that curvature is a property of the tangent bundle. The surface is just a way to implement a tangent bundle, not the other way around. Okay, although historically that has not developed this way, but eventually over time, especially in the 19th century, they realized that those kind of objects are much more primitive than other things. Okay, great. Okay, relatively decent pace. Okay? So if you actually do a field, and you can measure the rotation angle related to this connection, how much you deviated from just parallel, okay, then the field will, because it returns to itself, it will cancel the Gaussian curvature. The sum of rotations around every cycle will be 2 pi of the index, how many full rotations you did, and the cancellation of the Gaussian curvature. This cancellation is the trivial in trivial connection. Okay? And this totally carries to the discrete setting. You don't need any derivatives or anything like this. It's totally kind of a graph thing. Okay? Good. All right. So let's become a little bit more grounded in geometry. This was still kind of abstract, and talk about what we do on actual meshes. In fact, there are several valid choices that will all do these abstractions for you, but in different ways. Okay? So that's actually, I liked building it this way because a lot of the algorithms were classically defined on face-based field or on vertex-based field. But they don't necessarily need to be vertex or face-based field, like polyvectors or anything else. They can be defined anywhere as long as you just have this very, very basic tangent structure. So that's also the way I built it in code. There's like kind of an abstract tangent bundle, and then you instantiate it with a mesh to be face-based. So you can, if you invent a new representation, you can just follow those principles and then plug it in. Okay, so that's nice. There's a lot of different classes, but broadly, if we talk about triangle meshes, they divide into the 3 components of a triangle mesh: vertex, edge, and face, basically. So the one we usually turn to, although it's more kind of obvious, but not necessarily the most natural kind of stuff, is face-based fields, because we have kind of a natural normal, and every face is its own plane. So there's like kind of where we turn to. Usually piecewise constant, which means there's a single vector in the face, and it's like always the same vector when we define it. This is also one reason why we prefer this choice is also those are usually the gradients of piecewise linear functions, okay, naturally. So we correspond with this. The problem is that they're discontinuous at edges and vertices, and this can be sometimes a big deal. For instance, for fluid simulations or other stuff that needs stronger coupling, basically you can create a total noise and it will be a valid vector field. There's a lot of stuff in between that you don't want, like the full space of vector fields is not that great. It's too uncoupled, yes, too discontinuous. However, it's structure preserving, and I will only use it, I think, in this slide. I didn't want to talk about it so much, which means basically every vector field possible is the sum of a gradient of some piecewise linear function and some gradient of an edge-based function and some harmonic fields. That's usually classical in analysis that you want to do it. Or in non-formal language, every vector field on this is the sum of things that from sources and sinks, like divergent vector fields, and things that occur like vortices walking around, and something harmonic that is neither. It's just something that follows loops around surfaces. Okay? But that's the last time we'll do it on this. So, in face-based field, the tangent spaces, like instantiating that structure, are faces. The cycles are vertices, which means we measure curvature around walking around the vertices. The connection, yes, is literally just taking the 2D spaces that you define arbitrarily between faces and checking out how the mutual edge is defined between them and just dividing this. So you can translate between bases, nothing more than this. So those are in complex number, basically. And this reproduces angle defect, which means if you go walk around the face, walk, and you reach a holonomy in the first face, the angle is exactly the angle defect of the vertex. Okay? Meaning you reproduce everything on the surface itself. Okay? It's like opening this up to this kind of Pac-Man, if you know what Pac-Man is. Okay? And the missing part is the angle defect, if you develop it to the plane. Yes. Yeah, but actually they're not a full representation in the sense of singularities so much. Usually you use cycles inside faces. So you walk around in one face because they're changing inside the face. Okay, not going to discuss it a lot though. Yes. I wanted to mostly touch face and vertices. They're more... Okay. Vertex-based fields, which are very popular, a bit less because they don't have this kind of gradient structure, but they're very strongly coupled and very low dimensional because they're only 2V. V is the lower of V, E, and F, okay? So they're nice. They're good because they're very strongly coupled, they're usually kind of smoother. There's no like way to create things that are totally smooth and garbage in the vector field. The common flavor is to create some kind of vertex tangent base. It's either extrinsic, which means literally put some kind of plane on the vertex arbitrarily, and that's also a talk you will see later in SGP, and put some kind of normal on it, okay, and do something you want to do with it, or intrinsically, which means you have a vector that goes from the vertex and points inside the triangle mesh, and you parameterize the local cone around it. Okay, you like kind of do what means taking the logarithm map, like map this cone with some deformation to a plane, and then parameterize it there. Okay, so that means that the curvature doesn't exist on the vertex. It's no longer an angle defect in this sense. Curvature gets effectively pushed around in faces. By how much, it's not that obvious. You can just retrieve it from the connection that you're getting. Okay? What is the connection? If you indeed have an intrinsic space, if you have an extrinsic space, it's just a discrete tangent bundle for all purposes. There's nothing special about this representation. Intrinsically, that means two neighboring vertices share an edge again, and this edge is represented in 2D coordinates, in different 2D coordinates, and you just divide the difference. That's your connection. So that means the edge is parallel to itself in two neighbors. Exactly the same. Okay, and when you go around an edge and multiply those differences in coordinates, you get the curvature that got pushed around the face. All right. So I already explained this part. The cycles are indeed on faces, and the connection is the representation of the edge. So what's nice is that you can take any algorithm that works for face-based, like smoothest field, I will explain how it works, and do it on vertex-based, literally by plugging in all those components you need, cycles and faces. Okay, good. Exactly the argument of the connection. I will only touch a little bit of edge-based field. It's exists, but on the risk of insulting someone, it's not as mature as the other two in that sense. Yes, things like structure and singularities are not that well discussed, but it's still kind of a fascinating representation. What you have is basically kind of one vector per edge. It's defined in the middle of the edge, and the edge is what's important to understand is that the edge and what's called the flap, two triangles on it are flat. So you get as a flap a single coordinate system. There's an edge on it. It extends inside. And it blends between two different edges on the same triangle. So you're getting inside some kind of thing piecewise linear. So curvature is still inside faces, but it's also not continuous. It's non-conforming around it. It's a very nice structure because it kind of blends the non-conformity of face-based with some more continuity in the edge-based. So it's kind of something in between. Okay? There's also some structure to it, but we won't get into this. All right. Let's go into representation. Okay, we talked about discretization, the spaces we live on, but we haven't talked how to represent those objects in a way that we can do stuff on. Okay, so the classical one that is obvious is the one directional, the single vector field, what's also called a raw field. It's either Cartesian, which means you literally have just xy as one huge array per point, or xyz if it's on a volume. Okay, this we already discussed in some coordinate system. Okay, if you want the ambient field, the 3D one, you have to just multiply by the vector field that are the axes to get it. Okay? Or you can represent it in a polar representation again. It's just taking those logarithms, the argument and the magnitude. Okay? A Cartesian field has independent x and y, so you can do a lot of stuff with it, also gradients and things like this. If you need the unit length field, it's not that intuitive to work in Cartesian fields. Instead, in polar field, you just represent angles and you get automatic unit fields. What happens if we have an n-directional? So like the obvious choice is just get a raw field, like a list of those directional. The problem is that it doesn't carry any structure. Okay, like what's the matching in here? So one thing you can do is, given that the fact that they were always order preserving, is literally encode the matching by some integer. Okay, that was classical approaches were like this. They were saying I have a field, And this vector here goes to this vector there, and it's encoded by some PI that says if that vector here was 1, the first here and the second there, so the matching is 1. Okay? First go to second. Okay? But there's other ways to do this, and they're mostly, and I will talk about this now, cancel this difference. Like, don't encode the matching explicitly. Work with something that doesn't need to encode it explicitly. And those are also called power field. And they are explained better actually in the polar representation, though we're actually not going to be using that for that. So they're saying, okay, if I encode difference using some kind of integer multiple of 2 pi or something, which means like single click, 2 clicks, 4 clicks, yes? Instead, I can multiply everything by n and cancel the integer altogether, because I can take cosines and sines of them. This is called a power field. And actually, what's different about this is it doesn't encode any of the matching. It codes the entire 4 vectors as a single coherent unit. You want to get those 4 vectors back, you have to take the a cos and a sine, and then you have an ambiguity, and this ambiguity is exactly jump those 4. Okay? And that's sometimes good, sometimes no, depends. But that's called a power field. Okay. What happens if they're not symmetric? Okay, a power field is like a single number, yes, like a cosine sign that could also be e to the I of something, like a single complex number, but it doesn't represent those creatures. By definition, it doesn't represent those creatures because they have more degrees of freedom. Like if you think about it, a cross field has a single degree of freedom. There's like one vector, the rest are just rotations. Those have multiple degrees of freedom. How would you represent them? In a way that will also be coherent with applications. Okay, first of all, we want to represent them again in a way that doesn't care about matching because it's integer and it's nasty. Like we want to look at those 2 objects and say they're kind of similar. Okay, I want to know they're similar without knowing that 1 goes to 3, 3 goes to 4, and so forth. Okay? Like I want to represent them as single entities. So, basically, if we abstract this a little bit, you want to represent 4 quantities in a way that will produce those 4 quantities, but without meaning to order. The way to do this is use polynomials. Okay? So it means encode those entities as roots of some polynomial, a, b, and c, or 1, 2, and 3, or whatever, and then open it up, so to jumble the order, and collect the coefficients. If it's a complex polynomial by the fundamental theorem of algebra or something, it's bijective. That means the group of roots and the group of coefficients are bijective to each other, up to order, and that's exactly what we wanted. Okay? So you just collect those set of coefficients, and you use them as your representation. Those are the things you actually work with, instead of the roots. The roots you find out in post-process or somewhere in between when you need them. Okay, so that is the function we wanted. And by taking those roots, and since the roots are also, they're not entirely stable relative to the roots, but they're at least continuous and smooth, that means this guy and that guy, regardless to matching, will have more or less the same coefficients. It will be more or less the same polynomial. That's called an n-polyvector. Okay. Now, an interesting polyvector field, an interesting part about this, yes, is that, first of all, we use complex numbers to do all of this. Those are complex polynomials because they're vectors. It's much easier to do that. Otherwise, you have to have polynomials in rotation matrices and y. Okay, you don't want to. Okay, so the interesting part about this is if it's totally non-symmetric, you get 4 coefficients that are totally independent from each other. Totally 4 numbers. What happens if there's some symmetry inside? In fact, if you have some symmetry inside, the structure degenerates in a very, very coherent way. Okay? For instance, imagine that they're coupled in 2, where you have signs. Okay? That means every root also has a root in a minus. That means every odd coefficient just dies out. You can only use even coefficients. So instead of a polynomial of degree 4, you actually you masquerade it by a polynomial of degree 2 with squares. Okay? That's already very useful. We use them a lot. Okay? So if you take it even one step further, okay, if the field becomes totally symmetric, like a cross field, then all the 4 roots are rotations of each other, which means the polynomial totally degenerates to zeros except the free coefficient. And that free coefficient is literally just the power of 4 of that field. So it means the power field representation is just a special case of polyvectors. Okay? With a minus sign that is easy to get wrong, but that's just a technicality. Okay? Why does it matter? Because it means you can control how much fields are orthogonal, non-orthogonal, symmetric by linear constraints, by saying something wants to be 0. Okay, and that's actually a very powerful in a representation to be able to control. All right. There's other representations that we like or dislike, yes. So because usually they carry to 3D nicer, okay? So instead of representing a power field by the roots, we can represent it as some kind of tensor, which means instead of kind of representing it in a way that is this vector goes here, represented by the way it works on function, like as a function that says in this direction you have 1, in this direction you have 3rd, and so forth. So when you look at the entire function, it's a tensor. Okay, it's in 2D entirely equivalent, okay, to a power field at least, because it doesn't carry the symmetries. And the field is represented as a maxima. Why do we care? Because it's a little bit similar to power field representations. You can blend between them. Okay, so you can take one function and blend it linearly with another and get another, and the maxima will be the vectors you want. So it's another way to do something without order. Okay? And another interesting thought about this, because it's a function, you can represent it using circular harmonics. Okay, so you can say it's restricted, for instance, to band 2 or whatever, or you mesh it together, you blend it together linearly and it goes out of band 2, but you can project it to band 2. Once you create a representation for something that is not discrete but functional, continuously, you can do a lot of stuff that you couldn't do before. That's kind of the take-home message from the entire talk, actually. Okay. I would just say one word, that it's also possible to encode fields that don't have symmetry, okay, as some kind of what's called a quadratic variety, okay? That's basically kind of tensors that don't have this kind of symmetry. They have more degrees of freedom, but it's doable. All right. Now this was a lot of theory. Let's go into how we do stuff with them. So first of all, we touch objective. What do we usually want from a field? I've shown you some vector field, but I didn't tell you how I computed them, like what I did with them. So the most, let's call it primitive objective that we want from a field is to be as smooth as possible. Okay? What is smoothness? Meaning as parallel as possible. A field cannot be totally parallel because of Gaussian curvature, as I explained, but it can be as best as we can do. Okay? In angle-based approaches, that means the angles want to be as equal as possible up to some 2 pi difference. Okay? Compare matching angles. But in Cartesian complex approaches, basically, we're taking those representatives, either power or polyvectors, and we just compare them to each other to be as smooth as possible. Okay. So how do we do that? When we say smooth, we mean minimizing some what's called the Dirichlet energy. The Dirichlet energy is basically the norm of the gradient of a quantity. So if you want a quantity V, in which case our vector field to be smooth, you're minimizing its gradient. What does it mean here? You're minimizing deviation from parallelity. So a vector field I and a neighbor J, considering the connection between them, want to be as similar as possible. So this is the energy you're minimizing. It's a quadratic energy, means there's a single linear solution when you do this. Okay, where L is the connection ablation. That's how it's called for this. Okay? And you also add some kind of measure of metric or stiffness. That's an extra thing, which means you encode into the graph the actual geometry of the problem. So the similarity is not just uniform. There's some kind of metric on the edge that says how much you carry the uniformness of that, as how much stiff this should be. And this can be either depend on the geometry or application dependent. Okay, this is the connection itself, and this is the discrete connection operation. All right. One other objective afterwards that we usually use is orthogonality, which means you want to create the smoothest field, but if they're totally degenerate, you don't want them for meshing. It's useless. You usually want some kind of angle bound. If you use that for meshing, you want the quads to be as orthogonal as possible, like nicely well positioned and so forth, like also in here. So you also want to minimize the coefficients of the polynomial that are not the leading one, not the free one. Okay? Actually, the leading one. The free one is usually 0. Okay. Let's see, for example, for phase-based fields, how it goes. You get very simple expressions. That's something you can build at home. It exists already in Direction. There's a tutorial for this that you can operate. Okay, but it's a good exercise for grad students to do on their own. It's very easy to implement and view. Okay? The connection is simply the representation of edge in complex coordinate, one divided by the other. So you can, like, It's a little bit like having the edge being the mutual x-axis when you compare between them. Okay? So basically, the energy looks like that. Okay? You're saying two vector fields on every neighboring faces, f and g, sharing an edge E, okay, in complex coordinates, so all of those are complex number except w. You multiply by the conjugate of the edge, which means you're representing the vector field as if the edge is the x-axis in both sides, and this is an energy. Okay? You plug all those into a matrix that will look like L, and you just solve for LV equals 0 under some V's being known. And that will give you smoothest interpolation. That's something you can do at home. Okay, it's very easy, and there's obvious. What's nice about this is you obviously knew you did the right thing only if it works. Like if there's some bug, it will just show something terrible. If it will look smooth, you've done the correct job. There's no way to get this subtly wrong. Yeah. Okay. Now, what do we use for choice of edges? You could use cotangent weight, you could use a lot of stuff. Because it's dual, which means it's a face-based quantity and you go against the face, there's some more theorized versions. This is the one I like. It's the most stable. It's always positive. It looks weird. There's the length of the S squared by the division of areas, but it's basically the area of the diamond between the barycenters and the edge created. Okay, you connect barycenter, vertex, barycenter, vertex. It's a diamond, and that's this area. Okay, so it makes sense geometrically. Okay, once you computed this, basically what you're left with is some complex number for face. So now what? How do I get my vector field? Okay, and my singularities. So you need to do principal matching. You need to first figure out where the singularities are. Okay, to do that, you need to compute the effort, which means you computed this VE minus VE from the other, yes. It's non-zero, and now you're measuring how non-zero it is, okay? Basically, you're dividing what you computed against each other. You're collecting the argument that's this edge-based effort that you got. You add it up around vertices, okay? For parallel transport, if they're totally equal, you're getting a 0, okay? Because now, this looks like a complicated expression, but it is. This weird D0T operator is basically something that adds up things around vertices in the correct orientation. Okay, this is what's called the differential operator. It's a very simple operator to construct, and when you take the transpose, that is what it does. Okay, so you're adding the effort around the vertices, and you're offsetting it by the curvature that you know, the angle defect, times n if it's n. And when you divide by 2 pi n, yes, magically you're getting an integer if you did it correctly. That's, by the way, a way to debug it. If you don't get an integer, something is wrong in the way you did it. Okay, but you're supposed to. That's the index of that vertex. Okay. By the way, I said it in the speech of very face bells, but all of this works in every representation. You can just abstractify to tangent bundle. And then you get something like this. So if you put those crosses, those yellow ones, as degrees of freedom, you take them out of the matrix, you solve for Directional energy, you get automatically kind of a smooth completion of this to any non-red face. Okay? What I did on the right is have this alignment as part of the energy, like an extra term that wants to be like something, balanced with smoothness, so not exactly hard-coded, which you sometimes want. How do you do polyvectors? Exactly the same. It's simply more coefficients per face that you minus with each other. There's a small caveat with degrees, but I won't get into it there. You can look at the tutorial. And then, for instance, what you can do is put only one vector per face and interpolate it smoothly, including all the other vectors also to the other faces. And you get something that I don't know if you see here, but it's not a perfect cross field. You see, it keeps changing. Sometimes it smears, sometimes it doesn't smear. To fit better the fact that it is not a very isotropic surface. There's a lot of things happening that are not exactly quad-like. And those points you see are the singularities we derived by walking on every vertex. Okay? Good. There's no actual demo in here. That's misleading. But you can look up the demo exists. Okay, it's just time-wise doesn't make sense. Okay. What I wanted to do here is kind of the opposite. Go from singularities to field instead of the other way around. That's called kind of index prescription. Okay, so you put the singularities in place and assuming they match the index theorem, otherwise it doesn't work. Doesn't work means you're trying to solve a linear system that's going to be inconsistent. Okay, so you're getting something. So you're prescribing what's happening in the vertices, and you want to reproduce what's going to happen in the faces. So we're going to walk the other way around. You're going to compute the efforts, and from the efforts, you're going to be computing the field. Exactly kind of oppositely. Okay, so you get what's called a polar Dirichlet energy, which means for an existing sum over a vertex, like you know the budget in every vertex, you still say be as parallel as possible on the edges. Okay, that's still a smooth field with this. Okay, under the constraint that you have a specific budget per vertex on all the vertices. So basically, you're solving a quadratic energy with linear constraints. It's still a linear system. In fact, you don't even have to do this because there's a beautiful theorem on how to reduce this entire problem, but that's a bit of out of our scope. Okay, so that's what you're getting. You're getting the effort, and by the effort, you're just putting one vector field and walking around in a flat field manner to put all the other vector fields. Since you obey the constraint, it will match. Okay, it will be consistent around. So you don't have to fear about this. So what you can do, you can literally take this algorithm, put singularities where you wanted, up their indices, and you have to minus others. Also the genuses, and you're getting a vector field that will reproduce those singularities. So you can generate sinks and sources and so forth. Okay. Now, Polar allowed you to put singularities, which are nice, and Cartesian allowed you to do stuff, but it didn't allow you any control of the singularities. There's no in-between. One of the in-betweens that we usually do is what's called the Ginzburg-Landau energy, because one of the artifacts of the Cartesian method, yes, is that you compare, basically you kind of compare x and y's, okay? Which means it still compares magnitude that we didn't discuss so much. So it can cheat, which means if you try to put alignments that are very, very unlike each other, yes, it says, what's the problem? Let's take everything to 0 in the middle, or totally mash out the rotation, and once you normalize it, you suddenly realize you're left with a vector field that is not very smooth. So you were given singularities that were devised automatically, but they're not great. Okay? So we want to unmix magnitude with phase. But we don't want to go to polar fields because then we have to put the singularities ourselves, and we don't want to. Okay? So we want singularity to just be put in nicer places with a field that is more or less uniform. So this is where this comes in. Okay? Basically, it's the same energy, the same Dirichlet energy, except with a twist, also have an energy that the vector field wants to be as united as possible, which is nonlinear, with some measure of importance epsilon that wants to go to 0 as far as importance goes. So this is just Dirichlet, and this is the deviation from unit norm. Okay? So basically, if you're doing like bad alignment, you're getting this singularity party. Yes, because you did alignment that is like totally wild on the boundary, and it says, yeah, well, let's just, pack up a lot of stuff that are, if you didn't normalize, you just see them as zeros. It's like very smooth, but when you normalize, suddenly singularities pop up. Okay, and it's bad. So what is the effect of this energy, basically? It's like it's smooth everywhere. Okay, and at singularities, it kind of pulls out a ball, so the singularity won't create an explosion pole in the energy. Okay, that's the essence of this kind of thing. The optimization is very simple, but a bit hard to tweak. It's called MBO. MBO is the names of people. Forgot what. Okay, but it's look-upable. So it's a very simple algorithm. Instead of totally taking the smooth algorithm, you do one step of smoothing, like from some existing solution, like diffusion. Okay, and one step of projection, which means you take the field, you normalize it, and then smooth it again, and normalize, smooth and normalize. This is a bit like plasma works, and that's exactly why it's called the Ginzburg-Landau energy. It's physical. There's a bit of simulated annealing in here, basically. Okay, but after a while, the diffusion and the normalization kind of fit together because the normalization creates non-smoothness where the rotation is non-smooth, and it pushes the singularities away if you tackle it correctly. Okay, and repeat. Great. So I talked about alignment. There's not that much to say, except usually we use two types of alignment constraints, either full constraints, which means you put the entire quad in place, but that's usually not very intuitive. Usually you want to align to some features and some kind of curves. So someone draws a curve, you want the quantum mesh to follow that curve, like here or here, but you don't want to specify this is the U direction, this is the V direction, the artist doesn't care. It says auto-completed in some way. So usually what we have is like only partial alignment, and you have to have your field to implement this. Okay, this is actually very easy in those Cartesian methods, which don't care if you're this or that, because you're just saying, okay, This vector is one of the vectors. So I take the power of 4, and that's what you're supposed to align to here. And in polyvectors, you just reduce a root. It's very similar. But I won't get into the details. Another important constraint that I also touched a little bit is that of planarity. So you want to create quads, you want direction, but such that the mesh that you do will eventually be planar. The quads will be flat. So flatness is not an intrinsic property, because when you deform the mesh, it changes. It's an extrinsic one. Basically, if I have to intuit about this, what you want is that when you walk along one vector and then walk along the other, and then if you do the other way of walk, you reach the same place and they're all in the same plane. Okay? That's called conjugacy, and that's expressed by something called a second differential form, that you don't twist. That's actually a definition of the second differential form, okay? This conjugacy business. Second differential form of two vectors is how much you twist when you walk either one on the other. Yeah? So when you force this condition, you get things that are infinitesimally flat, the quad meshes, okay? But the problem is that you can only put one vector and the other one is already derived, so there's much harder constraint, okay? Because it's more. And then you get quad meshes that are planar, and it's even extendable to triangle meshes where every two directions are conjugate, and if you take a dual hex mesh, it's fabricatable, like from paper. Okay. Another interesting constraint, that's a problem that we worked on in the past and other people here worked on later, yes, is the Chebyshev constraint, okay, in which basically you want a quad mesh. It's relatively generic, except every edge has to have length 1. Why? Because it's basically kind of a network that's inextensible. You begin with some flat network, and you can take it up to space by deployment or some kind of fabric, but those will not extend. They will not become larger or smaller than unit 1. The only degrees of freedom here is kind of deployment and bending. Okay? And those networks are very physical objects, also used in stance, that you just have to use them in your design process in order to get, for instance, quad meshes that work. Well, the take-home message here is that the unit law is on basically the gradient. So if you design directional fields that will integrate into those things, you have to control the length of the directional. So using unit magnitudes is very important. Okay, that's a thing. So sometimes we want polar methods or otherwise. Okay. And now let's discuss one stage that I totally overlooked, but it's actually critical here. And that's how to go from directional fields to actual parameterization, that you do what you do. Okay? That's called integrability. So when we compute those fields, basically what we want them, not always, but basically is to be candidate gradients, which means we want to get some kind of scalar field, that the gradient will be the fields you computed in advance. So they will trace it. One necessary condition that this process of being candidate gradients will be error-free is that the field itself is curve-free. Okay? Meaning integrable. So you're getting a kind of what you see is what you get. And after our work in 2015, most papers had this kind of thing in the stage, because otherwise you may compute a beautiful directional field with a beautiful property. If it's not integrable, there's like an unbounded error in the parameterization, and there's nothing anymore, yes? So when you compute integrability, you have some credibility to the integration process. So you have this alignment, and then the parameterization will follow exactly what you're after. Okay, so earlier works didn't have that. They just computed a cross field. But the cross field on a triangle mesh is not integrable because there's no discrete isometric parameterization. So basically, if you looked at the parameterization, the integration after the field, you saw there was like a gross misalignment a lot of the time, especially in places where there was a lot of non-smoothness. And even worse, there were flipovers, like the parameterization totally flipped on itself because it wasn't controllable. So when you do something integrable, you're guaranteed perfect alignment. How do you work it out? Okay, what's curl? I didn't talk about this specifically, but why is curve-free related to gradient? Because of the differential property that the curl of gradient fields is 0. In fact, you don't want fields to be gradients, you want them to only be curve-free. Curve-free is a more important property than gradient because they're seamless, but I won't get into it so much. Okay? But how do you discretely compute this quantity? So if you have any piecewise linear function, what happens to its gradient? Because the piecewise linear function agrees on the edge, it's just a linear function of this edge, The gradient vectors also agree on that edge. The dot product with the edge is exactly this difference on the edge, this differential. So discrete curl is basically this difference. How much the neighboring fields agree on the edge. What do we do with frame fields? Exactly the same up to matching. So curl is not a property of the field itself. You have to do a matching, and it's a property of the matching, which is vector to vector, not the entire polyvector. Okay, so you created a matching, and to be curve-free, the matching itself has to be piecewise curve-free. Okay? Once you created a piecewise curve-free, when you integrate all those vector fields independently to n scalar function, those scalar function will be exactly what you see is what you get. Okay, so we're creating a concept of seamless parameterization, and how do we do that? Okay, there's a lot of text here, so I actually want to jump a little bit ahead, so time-wise. Basically, you're computing scalar functions like UV coordinates, okay, such that their gradients are the field. But to do that, you have to first match the field, create the singularities, and then separate them, which means cut the mesh along the singularities. So you can totally say this field is the U field, this is the V field, and they're totally separable, and then integrate them into separate functions using this Poisson equation. Okay? So it looks like this. You have a singularity, which means you cannot identify U and V separately. They're kind of intermixed with each other. To be able to do so, you cut the mesh along the singularity, like doing surgery. And then, by following the matching, you can identify them by different colors. Okay? So now there's just two vector fields once you cut out those singularities. Okay? And then you integrate them separately. Now, because the vector fields were curve-free and you took care of it, that even after the seam, they mesh with each other, what happens is that the U lines on one side and the V lines on the other side coincide. So the parameterization is seamless. There's a seam, there's an actual line passing here, but you don't see it because the U and the V kind of balance together with the period of the quad mesh. This is not only a thing that you can do in 4 fields, which will create a quad mesh, a full quad mesh. This is something you can do in 2 fields. This is a quad mesh from 4 fields, or I think this is 7 and 11 fields. The choice is random. So once you do that, you create the parameterization. You trace those lines, yes. Those are the UV lines of that parameterization. You don't see a seam anymore. The singularity, you see the singularity, but the rest is invisible. There was a seam passing here. It's just where the U and the minus U blended together exactly, seamlessly. Okay? And then you can just trace those lines and pick out, this is actual mesh from MeshLab. Okay, so this is a mesh with symmetry 4, the classical one, and this is symmetry 7, and this is symmetry 11, just for stress testing. Okay. I have about 10 minutes. I want to discuss a little bit the hardship of 3D. We won't get into this that much. Okay? It's just that everything is much worse, so don't do 3D. Okay? How does it work in 3D? Okay? You have a volumetric domain with a boundary omega. At each point, you have 3 orthogonal kind of out-order lines, so it's a 3D cross. It has what we call octahedral symmetry. Octahedral symmetry is because if you connect those dots, you get a octahedron. Okay? And you can flip it in all 3 directions, and it has this symmetry. Otherwise, matching and all those things still work the same. So if you have kind of neighboring things with a tangent bundle, you still have to say, this is a red goes to red, this is green goes to green, and so forth. This part is not the problematic part, exactly. Okay, so you can also dualize it and say those fields are actually kind of faces of a cube. So you can think about the field as kind of a field of cubes floating in space, where you can basically match the top corner of this to this top. You can define that those two are tops, those two are sides, and so forth to match. Okay, that's nice. That's the nice part. Now let's go to the bad part. Okay. First of all, before that, what are we using them for? We're using to do hexahedral meshes the same way we do quad meshes. We trace their directions, they have 3 directions at each point, and then you kind of take the cubes that follow those directions and get a single mesh that looks like this, and the topology of this mesh will be exactly the same kind of topology of this. So this is the hexes will go in this direction. So what are we losing when we're moving to 3D, except your sanity? So in 2D, singularities are very kind of nice points, +1 and so forth, okay, that look like that. That's because rotations are commutative, okay? You get a minus rotation, you get a plus rotation, they're cancelable with each other, so the index theorem is like very nicely put, literally just because the connection is symmetric. Like when you go to one point and then the other, you come to the same place. Okay, and then you get all those nice complex representations that you can just multiply and so forth, and polar representation with singularity control. Okay? However, you need triangulations to do that. Okay, that's fine. In 3D, though, rotations are not commutative. That's like the original sin here. Like all the other problems basically derive from that. Okay? That also, singularities are very diverse. Index theorem in 3D has an extra dimension, because it's also what's called the topological Betti numbers. Like, there's not only handles. There's handles in the sense of missing volumetric pieces, and there are handles in the sense of spherical pieces. So singularities follow suit. There's singularities that are pointwise singularities, like some on the inside, and there's curved singularities, like kind of cylinders that kind of extrude to the singularities. And they form a graph of singularities, and it's a very complicated creature. Okay, boundary alignment is non-trivial anymore, because you want a hex mesh, but the boundary looks like this. What do? That can be very nasty, and this is even 2D. You say, okay, no, let's put them nicely like that, maybe cut corner, but what if it's like a weird 30 degrees corner in like 3 dimension? Like, even visually, it's very hard to imagine what's the correct solution, yes? Not to say computationally. So those are very hard problems. Yes, and even worse, those orthogonal frames are never integrable because there's no conformal transformation in 3D. That's the reason. So you always have to use something non-orthogonal to survive. Okay? A classical representation that is like the most popular one, because this is the only one that shows some structure that actually works, is working in like I told you there's in 2D it's a niche to work with tensor, but actually in 3D that's the mainstream. Okay, in kind of a tensor representation. Basically work with 3D harmonics. That means works with a functional representation of a field as kind of a spherical function with extremas and so forth. Okay? So the classical function is x to the 4, y to the 4, z to the 4, gives you exactly the field in the original axis. And to get any other field, basically you apply a rotation matrix. Okay? It's in T because you actually apply to the original coordinates and then do the function by composition. Okay, then you can get all possible fields like that. So the only thing you have to parameterize is this rotation function. Except you want it without relation to order and without relation to all the other stuff, and that's where the difficulty lays. Okay? Previously, this was the complex number that you used, which was very easy, but now it's not anymore. Okay, so you want it to be order invariant. So what you do is basically create a representation that makes it order invariant. It uses spherical harmonics of degree 4. Spherical harmonics are basically kind of an eigenbasis of the sphere, like spectral functions that represent functions like a basis. Order 4 are functions of polynomial order 4. Okay, there's a class of them. Where basically the point is that the original function, yes, has those coefficients in the spherical harmonics. That's one of the points. Okay, great. That can be encoded. Fine. What about the other vector fields? That's one of them, okay? Any other possible octahedral field is represented by other spherical harmonics, okay? Where the spherical harmonics are all linear transformations of the original one by something called Wigner matrices. I'm using the word linear, but the Wigner matrices are not linear with relation to the rotation. That's a problem. And they will also never be because the problem is hard. Okay? So the problem reduces to finding those Wigner matrices and working with them. Okay? And they also don't have a closed form. There's an algorithm to compute them. So, yeah, I'm almost done anyhow. Okay? So basically, what all those algorithms do is they manipulate those 9 coefficients in spherical harmonic basis, yes, and then they project them to be Wigner matrices of that original A0. That's on one leg what happens in 3D. Okay? So every possible field that is an actual octahedral field will have this form. Okay, but how? The problem with this is that if you start interpolating those linear stuff, unlike complex stuff that you can just interpolate and then normalize if you wanted the unit field, here normalization is not that obvious. So if you're interpolating two spherical harmonic coefficients, you're getting something, some coefficients. And then what you have to do is project back to the space of Wigner parameterized forms, and this is local. I wouldn't say hard because there's an algorithm, but costly, okay, and not always very stable. Okay, so if you take, for instance, those fields and you interpret linearly their coefficients, you're getting something like this. Okay, so you need to project it back to the Wigner matrices. If you didn't stray too much, it's not that hard, but you still have to do this projection process. Okay, so there's a lot of derivations like this. This I won't bother you with. I just wanted to give you the principal thing. Okay, let's go state of the art is some semi-definite programming-based projection by Palmer et al., creating those kinds of fields together. Now, one class, actually the most popular class before we started working with those stuff, yes, is fields that are singularity-free. They said, okay, we want quad meshes, but without any singularities inside. Like they can be deformed into a single Lego piece, which is also called polycubes. Okay, and they are much, much simpler because there's no more singularities, no more matching. In fact, you don't even actually need the octahedral field because there's like a specific up, specific down, specific right. Not that it made this an easier problem, though. I mean, it made it an easier problem, not an easy problem. Okay, it's still a very hard problem to find correct polycube meshes, which means this representation that can be pulled back to a quad mesh. Good. That's my content. I just want to talk a little bit about challenges of all of it, okay, to cap up the talk. There's a few main challenges as I see them. One of the main challenges is none of those algorithms actually work. Okay, that's it, go home. Like, to work out vector fields, you need very good meshes, well-connected, correct connectivity, non-degenerate triangles, even a single degenerate edge in anything, or some slip, creates nuns that pollute the entire process and you're dead. That's not a problem of vector fields, it's a problem of finite elements, and all those methods were finite elements methods, so you're inheriting all the nastiness and worse, because you also need, it's more sensitive, because vector fields usually have less smoothness, so they're more sensitive to that kind of thing. So in meshes in the wild, even meshes that don't look like in the wild, like you look closely, it looks nice, but there's a weird singularity in here, and when you look closely, there's a rounding off error from some mesher that left triangles doing this. You try to create your vector field algorithms, it died, and you don't even know why. That's a problem, yes? Meshes can be solved in a second node water type, but even before that, why do you actually want meshes? A lot of the time you want to do simulations directly on, I don't know, MRIs, or do meshing directly on some stuff you get from scanners. Generating great triangle meshes to actually create other meshes is kind of cumbersome and not that important. We did this because this was an easy way to develop the program, but actually, application-wise, we want to be able to work on directional fields with some broken geometry in general, which we don't have. Okay, so most existing algorithms would fail. So interesting directions will always be some kind of ambient thing, either kind of creating envelopes around meshes and working on those envelopes, kind of stitching the mesh into kind of pillow tufted covers to be able to work with kind of missing pieces or things like this, or just working directly on level sets like implicits, which is like envelopes, but not exactly. But another, okay, so there's two learning slides in this talk, okay? This is not exactly learning, it's just neural, okay? Is if we can work on them in like perfectly ambient space or some kind of representation that is like not a triangle mesh at all, for instance, like a neural network or some grid-based stuff that will enable other applications that will scale better than working on meshes and will have more structures, okay? For instance, representing Jacobians as ambiently as a neural field that you can sample on triangles when you do them. That's a very interesting approach because it learns stuff triangle-free. So if you have any triangle mesh, you kind of get dropped from space vector fields instead of having to worry about adjacencies. The adjacencies happen ambiently. Okay, that's interesting. Or working on some kind of grid where the geometry is somehow in between, in applications like flow matching, which are by itself vector field-based applications. Or some work that we just published this year that we basically represent vector fields as some kind of temporal splines in space, okay, ambiently, instead of concretely on those triangle meshes. That's it. I just have a list here of resources. I don't know if you're getting the slides in the end, so otherwise you can just photo this. I use the citations from Directional, but there's a lot of other resources that do different things in directional fields, also different things I saw. So, and codes for all the individual papers mentioned. And thank you. Good time.
Hi, thank you very much for this course. I had a question, and that is if the fractional indexes on the 2D or the 3D directional fields have some kind of Poincaré-Hopf equivalent?
They have the same.
Exactly this one. It works perfectly.
Like it's just the mass is like a quarter, but you still need to add to 2.
Okay.
So for instance, as a very intuitive example, you want to mesh the sphere, right? Either there's a North Pole and a South Pole, 2. 1 and 1, yes? Or it's 4 corners of the cube, like 8 quarters, yes? And so forth, actually all the Platonic solids can be described this way.
Okay.
Okay?
Thank you.
Hi, Amir. Can you very briefly touch on the point you went quickly over about rotational seamless and the real seamless? Because I think for applications it's quite important, actually.
Right. Yes, because of lack of time and it being more mesh-wise, then I kind of glossed over it. So, seamless in the sense of vector field is what's called rotational seamless, okay? That means that you are doing the period, V connects to U, okay? But it doesn't mean that the same level set of V will be the same level set of U. They will have the same orientation, but with some kind of translation. To be perfectly seamless, there's an extra integer variable that you need to click together, which means you do the rotation correctly, and then you add another integer, so they will click together. Okay? That is not solved by directional fields. Actually, that can be solved by directional fields, but, future work. Okay.
Thank you very much for the nice class. I would like to know. If you have advices for choosing representation, because we have a lot of choices. I mean, Cartesian or
That's a very good question without a good answer, actually. Like a little bit like finite elements is a bit of an art. Okay, you first of all always need to think what your objectives are going to be. Like, what are you trying to do? Yes, like for instance, I put some applications here, like Chebyshev or stuff like this. So in Chebyshev, the prime thing is that you have to have unit norm. And then you think to yourself, what kind of representation allow me to use unit norm in a very intuitive way while still being integrable? So for instance, in all those stuff, we said, okay, let's use face-based fields with this Ginzburg-Landau thing that controls unit normness and with being integrable. And that's how you develop it, but it's not obvious. Like, it doesn't mean that you couldn't have done it better with like vertex-based or something. You just, think of, you need some experience with those representations and how flexible they are relative to your objective. Okay?
Okay, thank you.
Yes.
Hi. So if you rotate like a vector 2 pi, you get the same vector. You can have like pi over 2 rotations as well.
Yes.
But can you have 4 pi rotation field as well?
Including negative.
And it works the same way, except you have to choose the representation, right?
Yes.
Okay.
Yes. But
is there any use?
What I didn't touch here is that you have an interesting aliasing problem, which means if you're trying to force 4 pi rotations in a mesh with 6 things, yes, they will cancel out. Like it's going to be like this ventilator that rotates and you actually see it goes the other way around. You're going to see this artifact. Yeah, like you're going to see basically noise in the orientation, and this noise will arrange itself on the lower frequency rotation visually.
Okay, thank you.
So in order to actually encode those rotations, you need a lot of triangles, a lot of bases to be able to put it in small rotations around it. Okay, so enough sampling to be able to reproduce this.
Okay, thank you.
Sorry if I missed this, but if I have a polyvector field, can I optimize for integrability directly, or do I need to do this matching first?
Not in any way. Well, actually, in 2015, we did this with Polycur, yes? So it's doable. That was actually classically the way we did. The problem is other constraints. Usually, if you want only like an integrable smooth vector field, yes. If you start wanting Chebyshev and unit norm and smoking and all those other stuff, suddenly you need the matching. So it doesn't pay off to do this anymore. Like because if you anyhow need to do the matching somewhere in the algorithm, so it becomes a linear thing. So you do it on the fly with a keep changing matching. So in kind of more modern approach, we always used it up to a matching.
Interesting.
Was one over there? No?
Yeah.
Yes, you mentioned positive singularities.
Yes.
And what happens in the parametrization side when you have positive, for example, 1, when you try to do a for Rosy field? Do you have some insight into that? Because when they are negative, you will just get a singularity in the quad mesh. But when they become positive, then you have some kind of
just get 4 quads on a corner instead of 3 quads in the corner instead of 4. So a positive singularity means eat 1 quad. I think I mentioned this a little bit in the fabric case. A singularity basically is like you have a fabric divided by 4. A positive singularity is cut away one of them, glue them together. So you get a cube-like corner.
Okay, but
that's what happens in the quad mesh.
If I have -5, -6, I will have a lot of
more and more quads.
Yes, but if I do positive,
well, you end up at 2. Otherwise, it's degenerate. Okay. So half is the maximum you can do. Yes. Like
okay.
you get a kind of a pillow singularity, like with it closes end to end like that. Yeah. By the way, the reason, the algebraic reason why you cannot go anymore is because the Euler characteristic is 2 minus. So you can go negative as much as you want, but positive you're bounded by the sum. Yes, so you cannot do any better.
There are no more questions. Let's thank the speaker again.